So in the last lesson, we learned that if a molecule is polar, it had a good chance, well, not a good chance, it would have dipole-dipole interactions. And dipole-dipole interactions, you remember they're the second strongest intermolecular force, so they're very important. But we ran into this problem of how do you know in a larger molecule if it's polar and therefore can have dipole-dipole interactions? Well, you might remember that the key to it all is to draw a Lewis structure and then use Vesper theory to determine if the molecule is polar. Now, in this lesson, we're not going to talk about Vesper theory. We're just going to make sure that your Lewis structure drawing is in pretty darn good shape. Now, I find a lot of times people do remember how to draw Lewis structures, so we're going to let you try this out before we run through the lesson. And if you knock all of these out and get all these correct, then you're probably good to go and you don't need to go through the rest of the video. So therefore, in this video, I will have skipping turned on so that you can skip to the one you want to see if you get one particular one wrong. All right, so let's see. So here are the compounds that I want you to draw Lewis structures of. There's 6 of them, and the reason I chose these 6 is because they represent the variety of issues that people can have when drawing Lewis structures. So here are the answers. Now, when you're evaluating the quality of your work, I want you to look at some things. Some differences don't matter, and some do. For starters, if you had your oxygen going up instead of down, or if you had them more in a Y position, that doesn't matter because Lewis structures don't show shape. They only show how things connect together. Some things do matter though. For instance, you do need to have 2, 4, 6 lone pair electrons, right? 2 dots, and the 2 dots need to be paired together. You need to have 6 dots, so the electrons need to be properly drawn. The line in the middle represents 2 electrons. That covalent bond represents 2 electrons. Some people like to draw 2 dots there instead, but I don't. I don't draw it that way because I was an organic chemist by training and I typically don't, and I would say this is the more common way to draw it. So make sure all the dots are in the correct place, and of course this matters. In this first one, there should only be one shared double bond. All the others should be single. One of the problems people run across is they overshare electrons. Here, look to see if the 2 electrons are together. Now, it doesn't matter if they're over here, over there, but that lone pair of electrons on the central ones cannot be straddling a double bond. So that's the other thing. And there should only be one lone pair in the central atom. Look to see if you put lone pairs on the outside. This one should have no lone pairs at all. Check your hydrogens. They shouldn't have any lone pairs. This one should have 3 lone pairs. And it doesn't matter where you have the 2 on the top, or if you have 1 on the top, it doesn't matter. But you do need to have 3 sets of lone pairs around that xenon. So I'll let you check out the other ones. No double bond here. No double bond. And lastly, this one, no double bond either. And we'll get to each one of these. If you're not sure exactly why they turned out the way they are, then the next part of the video is we're going to walk through each one of these and figure out how their Lewis structures happened. Now, I will share with you my warning about this is students very often don't follow a series of rules that are really important to do in order. The biggest problem is sharing too early, creating double bonds when there shouldn't be. And the second biggest problem is putting electrons on hydrogen when there shouldn't be. So let's just start with the general rules. The general rules for drawing a Lewis structure are count the valence electrons, place the electrons around the outside atoms first. That's super important. Do not dive into the inside before you surrounded the outside atoms with electrons. And obviously all atoms are intending on getting 8 electrons, right? That's the octet rule. Once you've satisfied the outside atoms, then go to the inside and give the central atom an octet. The only time that you should ever create a double or triple bond is if you do not have enough electrons. Now, this business about formal charge we're going to get to a little bit later. All right? Now, the other things that will show up in here, and we'll just put it down right now, is remember that all atoms need 8 electrons, except for hydrogen, which only needs 2, boron, which only needs 6, and beryllium only needs 4. Sometimes people don't learn about beryllium and CP, but if you've never heard that, that's true. But if it's an atom other than carbon, nitrogen, oxygen, and fluorine, the ones in that sort of first row in the P block, for instance, xenon, sulfur, phosphorus, anything that's further down the chart, of course, those can have what we call an expanded octet. In other words, they can have more than 8 electrons, but only if they are in that third row, or further down on the periodic table. All of those can have an expanded octet. Okay, so let's look at how we figured out the answers to those. If you struggled with one, you can skip forward to it. If you're really struggling with all of this in general, then you're welcome to watch through the whole thing. So step one is to count the valence electrons. So you can see I've done that here in all of them. We'll look at a couple of examples together to make sure you have the right idea. But remember, on the periodic table, all of the atoms in the first column have one valence electron. These have two valence electrons. Skip the transition metals. Actually, they do have valence electrons, but they're not going to show up for what we're doing here because we're doing covalent compounds, right? 3 valence electrons here, 4 valence electrons, 5 valence electrons, 6, 7, and 8, like that. So sulfur, obviously, there's 1 sulfur in the compound. That's 6 valence electrons. Each oxygen has 6. There's 3 of them, so 6 times 3 is 18, plus the extra 6 is 24. You get the idea. Now, while you were looking at this, let's come down to here. You can see that nitrogen has 5 and hydrogen has 1. Well, there's 4 hydrogens, so 5 plus 4 is 9. But this was not the correct number because of that charge. So whenever you see polyatomic ions that have a charge, remember that if it has a positive charge, it means it lost an electron. Whereas down here, it's a negative charge, it gained 3 electrons. So instead of 9, it lost an electron. I'm going to use 8 for that one. All right? And then let's look at this one. Phosphorus had 5 according to our periodic table labeling. Oxygen has 6. 6 times 3 is 18. 18 plus 5 gives me 23. But that charge up there is going to tell me that I need 3 more. So I have 26 total electrons. You should always check and see if you're right. Have you noticed that all of the electrons are even in number? I am not saying that there are no molecules with an odd number of electrons. There are. They're called radicals. But generally speaking, you will not run into them in the AP curriculum. And so if you get an odd number, something is wrong, and pay attention to if it has charges. Okay, that's how we add up valence electrons. Now, how do we arrange the molecules? Well, you always put one atom in the center, and generally speaking, it's the atom that's sort of the odd one out, right? In other words, it's the one that there's one of that variety, right? So that's how you decide what goes in the middle. There are some difficult situations, like let me give you an example. If you were to have carbon, let's say nitrogen and oxygen, and you were trying to decide which of these went in the middle, the one that goes in the middle is always the least electronegative. In other words, fluorine never ever ever goes in the middle because it's the most electronegative, right? If you have carbon and fluorine, the carbon's going to go in the middle because it's the least electronegative. So that really is the official rule, but usually there's only one of that type anyway. But sometimes if you only have 3 atoms, that's the only way you can tell. The least electronegative goes in the middle. Okay, so we've got the valence electrons, and you remember that our process is always spread those valence electrons around the outside atoms first, so that you have 2, 4, 6, and remember in the bond is 8. I'm going to do 2, 4, 6, in the bond gives me 8. 2, 4, 6, I'm keeping them in pairs. I got a little sloppy there. So I've used 2, 4, 6, 8. Around each one, 8 times 3 is 24. I've used all of my electrons. I have none once. The oxygens have a satisfied octet, but the sulfur does not, and I don't have any more lone pairs to put on here. So you know what happens next. We can't walk away without sulfur having an octet. Right now it only has 2, 4, 6 electrons. It needs an octet, which means if the oxygens are satisfied and sulfur's not, an oxygen's going to have to share. So I'm going to come down here, I'm going to get my eraser, I'm going to pick on this oxygen, but it would not matter which one you chose, and we are going to drop those 2 down and put that pair in between to give us a double bond. And now the oxygen has 2, 4, 6, 8, satisfied octet. Sulfur has 2, 4, 6, 8, satisfied octet, and we are done. No more sharing. Nobody else. You might think it's unfair to that oxygen to drop down electrons, but nope, we have a satisfied octet. Do not share more than you have to. I'm not saying that it's a life lesson, but it's a Lewis structure lesson. Do not share more than you have to. Once the central atom has an octet, stop. Okay? So let's do the same thing around here. We have 34 to work with. I'm going to go boop, 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 boop. I I've spread my electrons around the outside, although for some reason I missed one right here. So I've got, oh, come on. I've got 8, 2, 4, 6, 8 around each bromine. 8 times 4 is 32. I have 2 left because I've only used 32. So then they have to go in the central atom. Now, if you're sitting here thinking, well, selenium already has 2, 4, 6, 8. It has a satisfied octet. It does not matter. Pick a space, either here, there, there, or there. I'm going to go right here this time. Oop. And put your 2 electrons. Oh, I don't know why they're disappearing. 2 electrons right there. And you've now used all 34. Yes, selenium has 2, 4, 6, 8, 10 electrons, but selenium is an atom which has an expanded octet. An expanded octet. And that's okay because it is in it is not in the first 2 rows of the periodic table. It's in the 3rd row down. We're going to stop right here and explain why that is. So what's happening is with selenium, what's happening is in the, let's see if I can draw a periodic table, is these atoms are filling up their p orbitals. And once they get beyond 8, you know that if you're in the 3rd row down, you're filling up the 3p orbitals. Well, what they'll do is, very similar in energy right in here, are the 3d orbitals, which are the very top line. And those 3Ds are very similar in energy, so there's a lot of room to pile electrons in there. The 2Ps cannot do that, right? Carbon, nitrogen, oxygen. And the reason is because there is no 2P. It would be right there, right? And there is no 2D orbitals, so there's no place to place those extra electrons. Little atomic lesson right there. All right, let's keep going. So here we go. We have not. No, we don't. We decided that was +1, so we took 1 electron away. We had 8, which seems more right. We go around the outside. What am I doing wrong right now? No electrons on hydrogen. Hydrogen has a satisfied octet with simply 2 electrons, and the reason is because if you look on a periodic table, it has 1 electron. It only needs 1 more to be isoelectronic with helium. So there you go. Oop. I might have switched pen colors, but that's okay. So we've done the outside. Hydrogen is satisfied. It's one of those exceptions. Then we go to the inside, and we've already used 2, 4, 6, 8. We've used all of them, and nitrogen has a satisfied octet, so it is good to go. Boom, we've done 3. We're doing a great job. Let's come down here. If I go around the outside of this one, I've got 22 to work with. Always outside, then inside. I've used 2, 4, 6, 8. Another 8, I've used 16, satisfied the octet of those 2 bromines. Now I've got a lot to work with, so they all go in the middle. 17, 18, 19, 20, 21, 22. All right, so we have used all of our electrons, and yes, xenon has 2, 4, 6, 8, 10 electrons. It also has an expanded octet. But that's okay, because it is not in the first 2 rows of the periodic table, and it can pile electrons into its extra nearby d orbitals, right? All right, now we're doing pretty good, but I want to pause here for a moment. It is customary in the world of chemistry, that whenever you have a lone pair, now you see this molecule has lots of lone pairs, but they're all in the outside atoms. There's no lone pairs in the central atom. But whenever there's a lone pair on the central atom, it's customary to put an orbital on it. Like that. So loop them in pairs to represent an orbital. Just customary. And the reason is because the shape is determined by those central atoms. You're going to see that's going to be useful a little bit later. All right, I'm going to spread electrons around the central atom of this one. I'm going to be blunt with you guys. I don't think I did a very good job. That electron's bigger than the other ones. Anyway, and I also, you can see like over here, it's hard to see the pairs. You want to keep them paired. Anyway, I've used 8 around each oxygen, and so that gives me 8 times 3 is 24. Ooh, I was about to say, wait a minute, I've only got 23. But that was before we dealt with the charge. Remember, a 3 negative charge gets me up to 26. And I've used 24, so that means I have 2 left, which is good because the phosphorus definitely needs an extra 2 electrons because it only had 2, 4, 6 electrons. It definitely needs that pair. And customarily, we put a little orbital on the central lone pair. All right, and then we do this last one. I have 24 to work with. There's no charge, so I don't get fooled by that. I'm going to go around and do the electrons around the outside. While I'm here and mentioning this, you see me just putting little dots because it's working best for me the way the computer is. It keeps giving me that little, it thinks I've right-clicked if I hang on too long. Be careful just sort of going around going doop, doop, doop when you're on a test because they need to really be able to see them. Anyway, 2, 4, 6, 8 around each chlorine. 8 times 3 is 24. I've used all of them. Now you come in here and I have none left to put on the central atom. And boron only is 2, 4, 6. Boron is not a happy camper because it got into this relationship because it wanted 8 electrons. Now you might be tempted to drop a pair down because you remember if you ever run out of electrons and the central atom doesn't have a satisfied octet, then you can at that point share a double bond, but once it gets 8 you stop. But remember, boron is an exception. Like hydrogen only needs 2, boron only needs 6 electrons. So it turns out this one is ready to go as well. But if it wasn't boron, if it was any other element that was in the center, you would need to share a pair of electrons down. So here's the takeaway of all of this. Count your valence electrons. Start on the outside. Don't jump to the middle. There is no shortcut. Shortcut is for suckers because those are the people who are going to get it wrong. Outside first, then inside. And once you get to that inside atom, do not share electrons down. Do not create double bonds unless you are 100% sure that that central atom has less than 8 electrons. If it does, and it's not boron, then you can share down a double bond, but not more than you have to. As soon as you hit 8 electrons, you are done. Stop there. All right, now this was step 1, which is learning how to draw Lewis structures. But this doesn't tell us whether they're polar or not, because I think, as you might be able to anticipate, the next part is to use Vesper theory to decide if the molecule is polar, and that's where we're headed to next.